Okay, so in chapter 2, basically we are going to understand what is atom and what are the molecules. And also we are going to talk about ions and names of these things. So we are going to name molecules and also talk about different types of molecules. So first we are going to talk about the word atom. Okay. So some Greek philosophers like Democritus believed that there was a smallest particle in any matter. So then scientists defined this smallest particle as atom. And the meaning of atoms is uncuttable. So we can't cut that atom into small pieces. So that's the meaning of atoms. So that made up all of nature. So every material has this particle. So experiments in the 80s and 19th century led to organized atomic theory by George Dalton in the early 1800s. So George Dalton he proposed a uh, theory. So it has 4 key points. And in his theory, he basically defined the word atom. So he come up with those points based on some of the experiments done by other scientists as well as by himself. So basically, in John Dalton's atomic theory, there are 3 laws, and those 3 laws are constant composition, conservation of mass, and law of multiple proportion. So we are going to briefly discuss those 3 laws. So the law of constant composition means if there's a compound, that compound always has a fixed ratio of atoms. So as an example, water. So composition of water is 2 hydrogen to 1 oxygen. So it doesn't matter where we are going to find water. It always has 2 hydrogen and 1 oxygen. So if it is different, it's another law. That's the multiple proportion. So it's a different compound. Compound have a definite composition. That means that the relative number of atoms of each element in the compound is the same in any sample. Okay? So if it is different, it's a difference in substance. So this law was discovered by Joseph Proust, and this law was one of the laws on Dalton's atomic theory. So second one is by Antonio Lavoisier. So this is the 18th century, I believe. So it's a good theory, and it's a valid theory. So total masses of substances present at the end of a chemical process is the same as at the beginning of a chemical reaction. So if you're going to do a chemical reaction, we always has the same type of atoms and same number of atoms. So it does not change. So basically, we can't convert atom of one element to an atom of a different element. So it is not possible and it does not happen in a chemical reaction. So that's the law of constant composition. So let me briefly give you a chemical reaction and explain this theory. So as an example, let's say we want to burn natural gas. So natural gas has this compound. So it's CH4 and it's a gas at room temperature. So this is called methane. That's a chemical name. And this is a key ingredient in natural gas. Okay, so composition of this compound is 1 carbon bonded to 4 hydrogens like this. So this is the composition of methane. So when we burn methane, like when we light a stove, it's going to react with oxygen from air. Oxygen is also a molecule because it has two different atoms. Yes, the oxygen is going to be a compound like this. So there are 2 oxygens bonded together by double bond. So there are 2 bonds between 2 oxygen atoms. So this going to produce carbon dioxide, and it's a gas, and water. Water is going to in the gaseous state, so that's why we don't see water when we burn natural gas. So carbon dioxide is a molecule with 2 oxygen and 1 carbon like this. So we already know the formula of water, right? 2 hydrogen and 1 oxygen. Okay. So as you can see here, in this chemical reaction, you have same type of elements in both sides of the reaction. So arrow is pointing towards the product side. So this side is called product. So products. So we can have multiple products or single product. So this side is called reactor or reactant. So we are going to talk about chemical reaction in chapter 3. So we will talk about all these things again. So what I want to highlight is the types of elements present in in this reaction. So we have carbon, hydrogen, and oxygen. So there are three different elements in this compound, in this reaction. The product side, carbon, hydrogen, oxygen in both. So we have all three elements in both sides of the reaction. So this is the beginning of a chemical reaction. This is at the end of the chemical reaction. So we have the same element. And also, if it's a chemical reaction, count is going to be same. So right now the count is not going to is not same, but I'm going to show you how it's going to balance based on the number of atoms. So in this, there's one carbon, four hydrogen, there are two oxygen. So these subscript numbers are the number of atoms. So when there's no any subscript for atom, by default it's going to be one. So it's one carbon, four hydrogen, and two oxygen. So that's how we count number of atoms in a molecule. So one carbon, four hydrogen, two oxygen. And right now, product side, we have one carbon in carbon dioxide, and there are two hydrogens in one water molecule, and one oxygen in water, and two oxygens in carbon dioxide. Altogether, there are three oxygen atoms. So now you can see it is not same because hydrogen and oxygen are not same on both sides of the reaction. But if it's a chemical reaction, these numbers are going to be same for all types of elements. So this is how it's going to balance based on the type of atoms. So when one methane molecule is going to burn, it produces one carbon dioxide and two water molecules. So two water molecules means we are going to get another water molecule. So now it's going to increase number of hydrogen into 4. And number of oxygen into 1, 2, 3, 4. So that's the number of oxygen. So now we have 1, 4, carbon and hydrogen is same, oxygen is not same. So we need another water molecule, oxygen molecule. So 1, 2, 3, 4. So there are 4 oxygen. So now it is same. So this was first identified by Antonio Lavoisier in 18th century. So at the beginning of a chemical reaction and end of a chemical reaction, we have same type of element and same number of atoms. So then the number of atoms is same means the mass is going to be same. So that's the meaning of law of conservation of mass. Any question? Okay. So basically the summary of this theory is atoms neither created nor destroyed during a chemical reaction. We are not going to lose any existing atom or we are not going to get any new atoms from a chemical reaction. So next one, we briefly talk about this theory. So law of multiple proportion. So if there are two different compounds made by the same two elements, then the lowest ratio or lowest whole number ratio between those two molecules is going to be different. So water is a molecule made by hydrogen and oxygen. So ratio is 2 to 1. So hydrogen to oxygen ratio is 2 to 1. So hydrogen peroxide is another molecule which has same two elements, hydrogen and oxygen. So in this molecule, there are two hydrogens and two oxygens, which means lowest whole number ratio is 1 to 1. So if this ratio is different, it's a different compound. So this law is called multiple proportion. So this is related to the mass again. If two elements A and B form more than one compound, the masses of B that combine with a given mass of A are in the ratio of small whole number. Okay, so this is discovered by John Dalton. And when two or more compounds exist from the same elements, they cannot have the same relative number of atoms. So that's a simple idea of this law. So based on all those experimental evidence, so John Dalton came up with these 4 key points, and it's called Dalton's postulate or Dalton's atomic theory. So first one is each element is composed of extremely small particle, and that particle is called atom. So that's the first point. As an example, if you have a piece of copper, the copper is an element. The copper piece has extremely small particle and that particle is called copper atom. Okay, so this is the smallest particle in copper. So this is called copper atom. So if it is a different element like iron is also has a particle. That particle is called iron atom. And it's also made from a small particle. That is the iron atom. It is true for any element. So that's the smallest particle which retain the characteristics of that element. So second point in Dalton's atomic theory is all atoms of a given element are identical to one another and in mass and other properties, but the atoms of one element are different from the atoms of all other elements. So as an example, let's say this is copper atom 1, this is copper atom 2. So copper atom 1 is identical. So when we write three lines like this, it's not equal, so it's identical. So it is identical by all properties. So the second copper atom. That is identical to the 100th copper atom. So if we take any copper atom from this sample, it's identical from every property. So if it is iron, all the iron particles are identical to each other. But it doesn't matter which number we are going to take, but it's always identical. But copper atom is not identical to any other atom. Okay, so we have like 180 non-elements. So copper atom is not going to identical or same or similar to any other element in the periodic table. Okay, so that's the second point in Dalton's atomic theory. And those two points in Dalton's atomic theory is not valid up to date. So based on the new experimental data, first 2 points is no longer valid. Let me explain why. Did anyone learn subatomic particles? So atom is not the smallest particle. So every atom is made of subatomic particles. So those subatomic particles are proton, electrons, and neutrons. So even we can divide proton, electrons, and neutron into another small particles. So that's why first point is no longer valid. So why second point is not valid? It is not valid because if we take different atoms from a copper sample, it is not same. So there are some copper atoms which has more mass. Okay. So we will talk about that later. So in a sample of any element, we have different atoms from that element. Like, so if you take a sample of carbon, so carbon has 4 or 5 different types of carbon atoms. So one has mass of 11, so one has mass of 12, 13, and 14. So if the mass is different, that is not identical. Okay. But it's still a carbon atom. Okay, so that's why second point is no longer valid. So these are called isotopes, and we are going to learn that later. Third point in Dalton's atomic theory is valid. So we talk about that. So atoms of an element are not changed into atoms of a different element by chemical reactions. So atoms are neither created nor destroyed during a chemical reaction. So if we have thousands of different types of atoms, we have exactly same 1,000 atoms at the end of the chemical reaction. So we are not going to lose any existing atom, or we are not going to get any new atoms from a chemical reaction. So atoms can change into different atoms, and those are not chemical reactions. Those are nuclear reactions. So that's what takes place in a nuclear reactor. So one atom can convert into a different atom. In that process, it releases large amount of energy. So this is about chemical reactions. So chemical reactions neither created nor destroyed existing atoms. So atoms of more than one element combine to form compounds. A given compound always has the same relative number and kind of atoms. So let's go back to the chemical reactions that we discussed. So atoms of one compound, So we have carbon and hydrogen. So we can, in a chemical reaction, these atoms can rearrange and form different compounds. So carbon and oxygen. So it is not same for any of the reactants. Atoms can rearrange in a chemical reaction to form compounds. And if it is a compound, it always has the same relative number and same kind of atom, like water, two hydrogen and one oxygen. Okay, so there will be one or two questions from Dalton's atomic theory. And also there are few questions in the next assignment. Make sure to remember those 4 points and understand those 4 points. Any question? Okay. So basically Dalton proposed a theory, or he basically defined the word atom. So he did not exactly propose a model for atom, but he just defined the word atom. So in Dalton's view, the atom was the smallest particle possible. Okay, so many discoveries led to the fact that the atom itself was made up of smaller particles. So after Dalton's atomic theory, some scientists did experiments to validate that theory. So when they do experiments based on the experimental data, they found that there are some other smaller particles. So those small particles are called subatomic particles. So there are 3 subatomic particles. Those are proton, electron, and neutron. Now we are going to talk about the structure of the atom. So basically, there are a lot of scientists who did experiments to find the structure of the atom, and one of the famous experiment is J.J. Thomson's cathode ray experiment. So J.J. Thomson made a small glass tube like this. So you can see that in this image. So in that glass tube, he put 2 electrodes. So these are basically metals. So he made a small glass tube and put 2 metals into this, like it. And then he sealed this after removing all the air. So we can vacuum this tube and remove all the air, or almost all air, and then seal it. So nothing inside of this glass tube. Then he applied a high voltage. So the voltage we have in our house is 110. So high voltage is something like 33 kilovolt. That's a high voltage. So this is 33,000 volt. Yes, it's a high voltage. So when he gradually increased the voltage of these 2 electrodes, so he observed a radiation emitted from the negative side of the circuit. So this is the negative side, this is the positive side. So in electronic or electrical diagrams, negative side is called cathode, and positive side is called anode. So it started from the negative side and goes toward the positive side of the circuit. And because of this, we name this rays as cathode rays. So this experiment is called cathode ray experiment. So later he found that these are not pure radiation. So pure radiation is like sunlight. So we don't have any mass in sunlight. So no mass, no volume. But these are not pure radiation like that. So this is due to a small particle in every matter. That particle is called electron. So this experiment led to find the first subatomic particle, electron. And then he modified this glass tube by putting different stuff in the middle of this glass tube, and he found that mass and charge of the electron. So electron is a -1 charge particle. The charge of electron is -1. Okay, so it has extremely small mass. Okay, so it is like I don't remember the exact value. So let's say 1 atom is 1. So it is like 1/2000. of an atom. So it's extremely small mass compared to the mass of atom. Okay, so and based on his experimental data, he proposed a model or structure for the atom, and that model of structure is called J.J. Thomson's plum pudding model. So this is the name he given for the model. So atoms are extremely small particle and it's spherical. Okay. And this has a mass. Okay. So that mass is evenly distributed. And there's a small particle in every atom. And this particle is called electron. It's embedded in the positively charged sphere in this atom. So this is like plums in a pudding. So that's why he named this model as plum pudding model. Any questions? So streams of negatively charged particles are found to emanate from cathode tube causing fluorescence. Okay, so J.J. Thomson is called with is credited for discovering 1897. Okay, let me go to the model. So the atom, the prevailing theory was that of the pudding model put forward by J.J. Thomson is it featured a positive sphere of matter with negative electrons embedded in it. So this is the plum pudding model. So this mass is positively charged, and those particles, extremely small particles, are negative charged particles. Those are called electrons. So then there was another scientist who wanted to validate this model, and that scientist is Ernest Rutherford. So Ernest Rutherford used one of the radioactive elements. So during this time, radioactive was a known thing. So it was identified by Henry Becquerel. Yes. So it was first observed by Henry Becquerel, and also Marie and Curie get credits to discover radium. So discovery showed that the atom had more subatomic particles and energy associated with. So there are some atoms which has more energy. So these atoms are called unstable atoms. So when there's an atom with a lot of energy, it's unstable. So atoms with energy or more energy, unstable. If it is an unstable atom, so this unstable atom constantly emits different particles or radiation. So that process is called radioactivity. So radioactivity is the process of emitting extremely small particles and energy from an unstable atom. So there are three main types of radiations. The types of radiation. So first one is alpha. So alpha is a Greek letter, and it's like this. Okay, so alpha is not 100% energy, so it's extremely small particle. So alpha particle is one of the known radiation during this time. The next one is beta. And beta is also a Greek letter, so it is something like this. So beta is also an extremely small particle. So this is due to high energy electrons. So these are basically high energy electrons. So electrons are negatively charged particles. So this has negative charge. So alpha is extremely small particle. So this is the nucleus. We are going to talk about nucleus later. So this is the nucleus of helium. So when we think about nucleus, so nucleus is the center of the atom. So nucleus by itself has a positive charge. So if it is the nucleus of helium atom, alpha is a positively charged particle. So that's a property of the alpha particle. And last one is the gamma ray. So when it says ray, it's a pure energy like sunlight, sound wave. So no matter, no volume. So it's a pure radiation, but these are extremely small particles. So there are other types of radiation, but these are the three main types of radiation. So in the next experiment we are going to talk about, it was done by Ernest Rutherford. So he used alpha particle because it's extremely small particle and it has positive charge and he gave charge of the alpha particle. Okay. So let's talk about the properties of charge particles. The properties of charge particles. So let's say we have two positively charged particles close to each other, like this. So what do you think? Is it going to stay like that? Two positively charged particles? No. So they don't like each other. So they repel each other. And it is true for two negatively charged particles. So always like charges repel each other. Or repel like charges. Repel each other. So if it is two unlike charges like positive and negative, this is like. So they're going to stay together. These two are like particles. So attract each other. That's the property of two different charge particles. And this is true for two magnets with south pole and north pole. So north pole doesn't stay together, so it's always repel. South pole repel, but north and south can attract each other. So electricity and magnetic properties are going to be same. So atoms contain suborganic particles, so protons, electrons, neutrons. So we are going to talk about these charges later. So this is what I highlighted. So how does this particles behave when it is close to each other? Okay, so now we are going to talk about, so these are the three types of radiation. So alpha positively charged, beta negatively charged. There's no charge, okay, I didn't give the charge of gamma and symbol. So this is the symbol of gamma and it doesn't have any charge. It's a pure energy. Okay, so we talk about the Clown-Pudding model. So now we are going to talk about Ernest Rutherford gold foil experiment. So he used thin gold foil in his experiment. So that's why it's called gold foil experiment. Okay, so the reason we use gold is highly malleable. So we can hammer it to get thin sheets. So we can get extremely thin sheets of gold, and then he assumed there's a layer of gold atoms in this sheet. Because thickness is extremely thin. So therefore, he assumed that it's going to be extremely thin layer of atoms on gold foil. So then he used gold, one of the alpha emitter in his experiment. So non-alpha emitter was radium. So he put a radium sample in a piece of lead tube and put a hole, and that hole is the direction of the alpha particle. So we can't see this particle, but you can direct it by using a small hole from a lead tube. So this is the radium, and it's an alpha emitter. So this is alpha particle. Okay, so then he directed all these alpha particles toward the gold foil. So now we have a beam of alpha particles like this. Okay, so I just enlarge it. So it's coming out of that tiny hole. And this is something that's a positive charge. Okay. So then, in order to detect these alpha particles, we can't detect it from naked eye. So what he used was a fluorescent screen. So when these alpha particles hit on a fluorescent screen in a dark environment, it creates some patches. So he can identify these alpha particles. So he used a fluorescent screen around this setup. So then he can move this fluorescent screen and get all these alpha particles. So based on this experimental data, what he observed was most of the alpha radiation penetrated through the gold foil and hit exactly on the opposite side of the fluorescent screen. So based on this data, he proposed a model for the atom, and what he proposed was atom is basically empty. because this is extremely small particle, so if there's something in this gold foil, it can't penetrate through this gold foil because two particles together should change its direction. When those two particles hit together, it should change its direction. Since these alpha particles are not going to change its direction, atoms are mostly empty. So that was his first observation. The atom is mostly empty. So nothing inside of this atom. And there were two other observations. So one of those observations was when there's alpha radiation, when come closer to the center of the atom, it changes its direction like this and it's deflected. So this is a very small percentage and like 0.001%. I don't remember the exact values. So you can see, so for 100, it's not like this. 1,000 for radiation, even it's less than this number, I guess. So it's like 1 for 1,000 radiation, so 1,000 particles, even if it's less than that. So based on this, he proposed that there's something in the center of the atom because this occurs when it is closer to the center of the atom. So there's something in the center of the atom, and this is a very small space compared to the size of the atom. So if this is the size of the atom, there's something in the center. And this should have a positive charge. The reason is when there's a positive radiation come closer to the center of that something in the middle, positive, reflect each other, and it can go like this. Okay. So that's the second observation. The center of the atom is positive, nothing inside of the atom, so it's mainly empty. The third observation was when there's a radiation goes through exactly on the center of the atom like this, it cannot penetrate through that center. It burns that like this and observe from somewhere here. Again, this is a very small percentage compared to the total alpha particles pointed toward the gold foil. So because of this evidence, he proposed that all the mass of the atom is going to be in the center. So it's very rigid and it cannot penetrate by the alpha particles. So all the mass is in the center. So this has all the mass. And later, scientists named this center as nucleus of the atom. Okay. And also some other scientists helped to discover the particles. And those particles were protons and neutrons. So protons and neutrons are in the center of the atom. And also the center has a positive charge. So that positive charge is due to the charge of the proton. So proton is positive 1. So neutron, no charge. And also electrons are in the atom. So electrons are outside of the nucleus. And because of its very extremely small in nature, any alpha particle doesn't going to interact with these particles. So it's extremely small compared to the size of an atom. And also when you compare the size of an atom to the size of the nucleus, so if you want to compare it to real world examples, you can take the size of the atom as a soccer field, and then center is going to be like the soccer ball in the center of the field. So that's the size comparison in real world. Okay, so based on that, Ernest Rutherford proposed the model. So that's a center, and that center is called the nucleus, and it's extremely small space. So 1 to 5 angstrom is the size of yes. Okay. The atoms are very small, 1 to 5 angstrom. So 1 angstrom is 10 to the power negative 10. 1 angstrom is 10 to the power negative 10 meters. The angstrom has small dot on top of it. So that's how we write angstrom. So you can see it's a very small particle. And when you think about the size of the atom versus size of the nucleus, so these are the numbers. Size of the atom is around negative 10 meters. and nucleus negative 15 meters. So it's divided by 100,000. So that's the size comparison. So Rutherford postulated a very small dense positive center with the electron around the outside. So that's Rutherford postulate for the atom or the proposed model. So most of the atoms in this space, atoms very small, and other subatomic particles, proton and neutrons in the nucleus were discovered by other scientists. So protons and neutrons are in the center. So when we think about a material, so this is real world. So this is what we see from our naked eye. So this is a piece of lithium. It's a soft metal. So in this soft metal, there are millions of atoms, or even more than, like it's a very huge number. So these atoms are well organized. So we talk about the arrangement of solid particles. So if we enlarge one of those atoms, so there's a large empty space in an atom. And there's extremely small center which holds all the mass, and it is called nucleus. And this nucleus has two other subatomic particles, those are proton and neutron. Any question? Okay, so we talk about two different experiments, J.J. Thomson's plum pudding model and Ernest Rutherford Goldfield experiment. So I have two nice videos on Blackboard. So let me play those two videos. So these are the modern version of those two experiments. So I think it is really cool to see. It's in the module 1, chapter 2 folder.
So today I'm at the University of Sydney with Dr. Phil Dooley, and we're talking about how our idea of the atom changed from a tiny little hard sphere to something more complicated. And this apparatus has something to do with that.
Exactly. It was quite a landmark historical experiment. It's just made of a tube of glass connected to a vacuum pump, and in the tube of glass there are two pieces of metal connected to a high voltage power supply.
So we can suck the air out of here.
That's right.
And then apply high voltage to two metal plates.
Yes. Normally with high voltage in air, we don't get anything except maybe a big spark. But what Geissler found, who did this in 1857, was something quite different. So should we have a look?
Let's do it.
Okay, let's turn on the pump and the high volts. Turn off the lights so we can see what's going on. As you can see, something's happening now.
Yeah, I see a bit of a pink glow in there.
That's right. So imagine Geissler, the first person to ever see this. Pretty surprising. That started people thinking, what is this stuff that's coming from the cathode? It seemed to be a ray emitted from this negatively charged one, which they called the cathodes, therefore it's called a cathode ray. And it became the topic for research for the next 40 years as all the big wigs of physics and science basically tried to work out what was going on.
So what did they figure out? I mean, what is going on? What's producing this this glow here?
There were two main camps. One thought that it was waves, and the second thought that the electricity was being carried by a stream of charged particles. Over the next 40 years, they basically came to the conclusion, well, it was J.J. Thomson in 1897 who came up with the idea that there is a stream of very small charged particles, negatively charged. They're smaller than an atom. So the smallest atom, hydrogen atom, they're about 1,000th of the size of that. And it doesn't matter what material the metal is, it's always the same particle. So this particle appears to be in everything. Yeah, this electron, as it was known, is what's carrying the electricity.
So Thomson came to the conclusion that all atoms had this particle as one of their constituents.
That's right. So it wasn't a billiard ball. There had to be something inside the billiard ball.
So how do I picture like a billiard ball with bits inside of it?
Well, you should probably think about a pudding.
Pudding.
Yeah, well, that's what his idea was, that it was a plum pudding, very dear to every British person's heart.
Right.
That, and inside the pudding you have plums. And plums can come out of that. So when you apply high voltage, then a negatively charged electron, which Thomson pictured as a plum, comes out and leaves behind positively charged pudding.
Are you a fan of plum pudding?
For research purposes, definitely.
All right, well, let's see if we can research this a little further.
Okay, that sounds like fun.
Okay, so let's go to the next one. So this is the Ernest Rutherford Gold file experiment and the modern version.
Building your online business? Go to Wix.com and set up your store on a single integrated platform. Add products. Show
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now, Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be nuclei of helium atoms, through a very thin gold foil. The brass can in the center of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom is empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. It becomes a glancing blow, which deflected through a small angle. Hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behavior of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometers in circumference.
So as you can see, based on those two experiments, so something we believe today can be wrong in another 50 years or maybe another 10 years. So science is always updating with new evidence. So plum pudding model was a valid model for a longer period, but after that, so this is the structure of the atom. So still, there were a couple of other models proposed after Ernest Rutherford model. And we are going to talk about the exact location of this electronic atom in chapter 6. So that's the arrangement of electrons. So for most of the time, I will use this model, and we are going to think these electrons are on different energy levels. We will talk about the exact location of these electrons in like chapter 6, but these electrons are going to be on different energy levels in atom. So there's an allowed place for these electrons in an atom. Okay, so now we are going to talk about the subatomic details in subatomic details and their properties. So these informations are important because next lecture is going to be based on all the information that I'm going to write here. Okay, so we have three subatomic particles. So these are the particles. Okay, so next one is simple. Next one is mass. Next one is charge. Next one is location. So where this subatomic particle in an atom. So first one is going to be proton. Okay, so most of the time proton symbolize using simple P or P plus like this. So P plus stands for the charge of the proton. So this symbol is more close to the actual properties of a proton. So proton charge is going to be +1. So what is the mass? So when it comes to mass of these extremely small particles, these are very small values. So we can't use a unit like kilograms or Kelvin. So because it's not practically possible, because mass of a proton is somewhere around 1.66 times 10 to the power -27 kilogram. Okay, so we have 26 zeros at the beginning of this number. You can see it's extremely small number. And because of that, we're going to use a different unit. And this value is equal to the new unit, which is 1 atomic mass unit, AMU. So AMU stands for atomic mass. And also there's another abbreviation for atomic mass. So the symbol or abbreviation is going to be AMU or infinity. Okay, so I may use both of these. Just want to let you know because sometimes I will write U because it's short. The atomic mass symbol is using U, so AMU. So now you can see mass of a proton is this number, and we call it as 1 AMU. Okay. So atomic mass unit defined, it's derived based on the mass of a carbon atom. So it's 1/12 of a mass of a carbon atom. C12 times carbon atom. So that's the definition of 1 AMU. So location is nucleus. So it's in the center of the atom. So next one is neutron. Okay, so before that, let me quickly give you the exact value. So this is the rough value. Okay, so it's close to 1 atomic mass unit. The exact value of a proton is 1.007 atomic mass. So you can see it's 007. So we can drop the 007 and consider as 1 atomic mass unit. So this is the value you need to remember. The 1 atomic mass unit. Neutron is the second subatomic particle. Neutron symbolizes using N. For its charge is 0, no charge. N or N0 is a symbol for neutron. And the exact value of a neutron is 1.008 AMU and no charge. Let me quickly finish this. And again, location is nucleus. Again, 1.008, we can consider mass of a neutron as 1 AMU. The proton and neutron almost equal in mass, but in reality, neutron is the heaviest subatomic particle. It's slightly heavier than proton. The next one is electron. Electron symbolized using E or E negative. And mass of a electron is exact value is 0.000549 AMU. So if we drop 008, then definitely we can drop this and consider mass of an electron as 0 AMU. So electron is a -1 charge particle. Location is outside of the nucleus. Okay, so when you come to the next class, please remember these numbers. So next lecture is going to start from this one. I'm sorry, I took one.